Hi, welcome to the 11th session, or is it 12th? Anyway, of inner product spaces. Today we are going to talk about orthogonal linear maps, which are known as orthogonal or unitary maps. Usually textbooks, since they restrict themselves to complex inner product spaces, they will talk about only unitary maps. But for geometric reasons and real life computations, orthogonal maps are also equally important. Okay, and so we will have a quick look at, and the results are identical. You don't know to sweat any more to deal both together. Okay, so let's get started, and I hope that this will be a short lecture. I don't want to spend too much time on that. Yeah, so let V be an inner product space over a field F, which may be R or C. Okay, right. And suppose W is also one such. Okay, two inner product spaces. And suppose F is a linear map from V to W. Okay, so when I say it's a linear map, it kind of respects the vector space operation, namely vector addition and scalar multiplication. But now remember, V and W are extra structure. What is this extra structure? Namely that they have an inner product. Alright, so I would like to know how does F behave with respect to inner product. So in other words, okay, think of this over R. Therefore I have two vectors here, V and another vector W. Then this may be, maybe we should call it V1 and V2, and okay, this may be f of V1, this may be f of V2. Okay, this is W, this is V. What I can ask for is what happens to the angle between them, what happens to the length, because V and W are extra structure. Alright, what is the, how the length of V1 and length of f of V1, how are they related? Similarly, f of V2 and V2. And not only that, in the case of real inner product space, I can ask about what happens to the inner product or orthogonality in the case of general complex numbers. Right? If V1 and V2 are orthogonal, does it happen that f of V1 and f of V2 are orthogonal? So all these questions can be very simply answered if I know something. Can you guess what it is? By now all of you have seen already group theory and kind of maps, okay, group homomorphism, linear space, etc, etc. So you should preserve the structure. What does it mean? If I have V1 V2 in V, then I have the notion of V1 V2, the inner product, and similarly I have the notion of f of V1 and f of V2. So if I want to know my f preserves the length and the angle between them or the orthogonality between them, what is that I have to ask for? I should ask for this question. For every V1 V2 this happens. Right? So I say then f is inner product preserving. Okay, is that clear? Okay, now suppose we restrict we ourselves to V to W. Okay, but before that let's look at, if suppose f is inner product is preserving, okay, what can you say about the kernel of f? Because what is kernel of f? It's a vector V such that f of V is 0. Right? But first notice that if whenever inner product V1 V2 equal to inner product f of V1 f of V2, it follows that f of V, now length of this equal to length of V for every V. Because take V1 equal to V2, therefore norm squared of V1 is same as norm squared of f of V1, and hence this equality holds. Right? Therefore the length must be preserving. Okay, this immediately says if V f of V is 0, that is if V belong to kernel, then norm of V must be 0, because this is 0. Norm of f of V is 0, Therefore, norm v is 0. That means v is 0. So what can I conclude? If f is inner product preserving, then f is 1 1, a linear map. Isn't it great? Good. And now can I do something more? Yes. Suppose dimension of v is same as dimension of w, and both are finite dimensional now. Okay, so far I never assumed it's finite dimensional. Do you see that? Go back to the earlier statement. I never assumed v and w are finite dimensional. They are only inner product spaces. Now suppose they have the same dimension, okay, and f is inner product preserving. Right? Then f is 1 1 linear map. So what can you conclude? You must have seen it. For example, from rank nullity theorem, it follows that dimension of f of v, okay, plus dimension of the kernel of f must be equal to dimension of v. But this is 0. Therefore, dimension of f of v is same as dimension of v. But that means the same as dimension of w. But f of v is a vector subspace of w having the same dimension. Therefore, I conclude f of v equal to w. Okay, you see that? I again go back to the same thing. Whenever something happens, I simply don't say f is onto. How did I prove it? I go through the proof in mind. Okay, this is it. So, what have we concluded? If dimension of v equal to dimension of w and f preserves inner product, then f is a linear isomorphism also. It is onto. Okay, this is a corollary we got. Okay, very good. Now let us specialize further. Suppose v equal to w. Alright? Okay. In that case, I claim, okay, if f is a linear map from v to v, okay, and inner product preserving map which preserves inner product, then we say f is orthogonal linear map if the ground field f is R, or f is unitary map if it's a complex inner product space. Okay, let us quickly make a definition in case you miss the point. If f is from v to v linear, it's a orthogonal or unitary if for all v and w in v, f of v inner product with f of w is same as inner product vw. That's it. Okay, now again notice that we are assuming v is now finite dimensional inner product spaces, inner product space. Therefore, this shows that f is a linear isomorphism, as we saw earlier, right? Pause, review, and proceed. Okay. Now the question is, how do I produce, okay, how to generate or produce orthogonal or linear map, orthogonal or unitary maps. Yeah, remember, if f from v to v is linear, if it's known, as soon as I know its action on a basis, right? If vi is a basis of v, Then if I know what is f of vi, then I know what is f. But remember, now V is an inner product space. So what is the next question I should ask for? I should look for an orthonormal basis. Suppose u1, u2, un is an orthonormal basis. B, okay, and suppose f is inner product preserving, that is orthogonal or unitary. Notice that it does not matter what the field is for this. Okay, then what do I know about f of u1, f of un? This set. Remember, if it's inner product preserving, that is orthogonal or unitary, it's a 1-1 map. And as you should remember, any 1-1 linear map carries a linearly independent set to a linearly independent set. Therefore, this must be linearly independent set. Do you agree with that? Right. And how many are there? They are n in number. But what is the dimension of V? That's also n. Therefore, this must be a basis of V. Right? That's very easy because it's pure linear algebra, first part of linear algebra. But I still have not used the fact, okay, f is inner product preserving, un though, because whatever I said about u1, u2, un will work as long as f is a linear 1-1 map. Okay. Now what do I know about this? Now I know f of ui, inner product with f of uj, is nothing other than inner product ui uj, which is delta ij. Therefore, this shows, okay, this collection f of ui 1 less than equal to I less than equal to n is an orthonormal set. Yeah, but do you remember? And none of them can be 0. F of ui for all I is not 0. For all I. Right? Why? Because norm of f of ui must be norm of ui, which is 1. Therefore, f of ui cannot be 0. Do you agree? Therefore, we know this is linearly independent. Okay, we are give another proof. Okay, and hence this is orthonormal basis. So what do you think I have proved? So we conclude f from V to V is orthogonal or orthogonal or unitary linear map. Then f carries an yn basis, orthogonal basis of V to an yn basis of V. Okay, pause, review, proceed. Right? Have you understood? See, this is not the way you look at in textbooks. As usual, we are just playing with the notion, okay, so that we become confident. Have you understood? Our question was how to generate orthogonal or unitary linear maps. So what was our cue? I know linear map as soon as I know its action on a basis. Now since I am in inner product space, so what should I ask for? If I start with an orthogonal basis, what happens to its image? We found out it's an orthogonal basis. Right? What is the next question you should ask? Yeah, suppose f is a linear map from V to V which takes an orthogonal basis to an orthogonal basis, then what should I ask? Whether it is unitary or orthogonal. Is the question clear? So is the converse true? That is f from V to V linear and takes an orthonormal basis to an orthonormal basis is f orthogonal or linear, orthogonal or, see, I don't know why I am saying orthogonal or unitary or linear map. This is a question. Have you understood? Let us look at what is that I have to check. Now, suppose I start with a vector b. Okay, I write it as summation xi ui and start with the vector w, which is summation yj uj j equal to 1 to n, I equal to 1 to n. Okay, let ui be an orthogonal basis. Okay, write v and w like this. What am I supposed to show? I have to show is inner product vw equal to inner product fp fw. Right, it's already a linear map. I only have to check this. Is it clear? Right? But if I had followed my lectures, you know what is inner product BW? What is inner product BW? This is nothing other than xi yi bar. Yeah? Why? That's because inner product xi ui, I am again as usual doing it for your sake, wj uj, this is going to be summation over inj. You know, okay, it's linear in the first variable and conjugate linear in the second variable and intuitively distributive law, right? So it's xi yj bar into ui uj, but this is delta ij, therefore it becomes xi yi bar. Is that clear? Right? Now what is f of v? F is linear and therefore it's f of summation xi ui, that is equal to summation xi f of ui, right? Okay, and what is f of w? For the same reason it's yj f of uj, right? Okay, now what do I know about this collection f of ui? By hypothesis, this is an orthogonal basis. Therefore, this vector is written as a linear combination of orthogonal basic vectors. Similarly, f of w. Therefore, I know what is f of v, inner product f of w. Do you see that? This is an orthogonal basis. Therefore, this is nothing other than, again for the same reason, xi yj, j bar delta ij inj, which is equal to summation xi yi bar, I equal to 1 to n. Do you understand this? Okay, whatever be the orthogonal basis, if I write a vector as a linear combination, another vector as a linear combination, then the inner product of these two vectors is nothing other than the standard complex inner product on Cn or the dot product on Rn. Do you remember? Yj bar will be yj if the field is real. Please understand, this is why you want us to work through. Okay, so what I have shown now? I have shown that if I have a linear map which takes an orthogonal basis to orthogonal basis, then it is orthogonal map or unitary linear map. You understand? Okay, therefore we have proved a theorem. What is the theorem? Let f from v to v be a linear map. Okay, where of course v is a finite dimensional. Let v be a finite dimensional inner product space over f. Be a linear map. Assume, okay, then f is orthogonal or unitary if and only if it carries or takes an orthogonal basis of v to another yn basis. That's it. Okay, pause, review, proceed. Now, do you think we have answered the original question with which we started? So, what are the original question we started with? If V is a finite dimensional product space, how to create a unitary or orthogonal map from V to V? Now, what is that we have proved? We have proved if F is any linear map from V to V which carries an orthogonal basis to orthogonal basis, it is unitary or orthogonal, right? How does it solve our problem? Answer is easy. Why? Because what all I have to do, remember, a linear map from V to V is determined as soon as I prescribe, okay, what is the action of F on a basis. Alright. Now what I can do is I start with an orthonormal basis, let us call it U1, U2, Vn of V, another orthonormal basis V1, V2, Vn of same V, and define f of ui equal to Vi. Okay. Then there is a unique linear map with this property. By very definition, that map must be orthogonal or unitary. Do you get it? Should I write it? I will do it. Okay. So the idea is, let V be finite dimensional inner product space and ui and vi be yn basis V, right? Then let f of ui equal to vi for 1 less than equal to I less than equal to n. Then extend f. How do I do that? We know that there is a unique linear map with this property because these are all bases. This is pure linear algebra of the first part. There is no inner product, right? Okay, there is a unique linear map so that f of ui equal to vi. Okay, right. So how do I do that? Just to be on safer side, let me go. If I write x v equal to xi ui, then f of v we define to be xi f of ui, because if f is linear it must be true. But what is f of ui? It is xi vi, right? Therefore I know how to define that, right? So if my vector v is summation x1 u1 plus xn un, okay, under f where does it go to? x1 v1 plus xn vn. Okay, and you can, this is a linear isomorphism, easy. It's a linear map is good enough for me. Now notice that, okay, now this is a linear map. This linear map carries ui, the an orthogonal basis to another orthogonal basis vi. Therefore f is orthogonal or unitary. That's it. We have solved the problem. Yeah, think about. Now that we seem to have answered the question, what is the next question I should ask? Come on, how do I generate orthogonal basis? That's again easy. How? You start with any of basis and Gram-Schmidt process gives rise to an orthogonal basis. Alright? Therefore, I start with the basis, let us say, call it v1, v2, vn. Okay, then I get orthogonal basis u1, u2, un, and start with another basis w1 to wn. That gives rise to another orthogonal basis e1, e2, en. Just e1, e2, en, just for want of notation. This is not standard, okay, for any inner product space. Therefore, I produce. Now, do you want to ask another question? Go back to my linear algebra basis. How to construct basis in finite dimensional spaces? I have shown that to you. Because next question is, okay, if I get two different bases of the finite dimensional space by Gram-Schmidt process, I get two orthogonal bases, and hence I can construct orthogonal or unitary linear map. Very good. But how do I get a basis? Different bases. Go back to my video on construction of bases. Okay, usually that's never taught. You will see that. Okay, so we have done that. Okay, right. So this is how we are done. All right. Okay. So is there anything more you want to say? So what I have shown is the following. Okay. Now there is another interesting theorem. Okay. Maybe with that I will stop. Suppose V is a finite dimensional inner product space, and F from V to V is a linear map. Now we have shown that if F is orthogonal or unitary, then for all V in V, norm of F of V is same as norm of V. Right? Now I can ask a converse question. Okay, like now the converse is, if for all V in V, if norm of F of V equal to norm of V, can I conclude F is orthogonal or unitary? The theorem says yes. So this needs to be proved. Okay, pause, review and proceed. This is highly non-trivial theorem. The proof is easy, but you should understand. Okay, this is non-trivial. Why it's non-trivial? How do I get this norm from the inner product? Right? So it's a linear map which preserves the norm. Okay, instead of preserving inner product, it preserves the norm. That simply means it preserves the distance from the origin, the zero vector to the vector. Right? D of 0 V is norm of V. So it preserves this distance. That's it. From that I want to conclude F is orthogonal or unitary. Do you like it? Think about it. Okay. Now how do I prove that? Okay. Now if you had been following my lectures on inner product space, you know that what is that I have to prove? It preserves inner product. That means I have to prove for every V W in V, I have to prove F of V, inner product F of W is inner product V W. This is what I have to prove. Right? But what do I know is this: norm of F of V is norm of V for all V. Right? So what do you think I should do? You know that, right? So I want to talk about, I know something about norm X. How do I get about something about inner product XY? When we defined Cauchy-Schwarz, when I proved Cauchy-Schwarz inequality, I already said the trick is, yes, you have to use summation X plus Y. Right? So let's do that. So at present, let me assume F equal to R. Okay, F equal to C. I will indicate the proof later. Right? So let us start with two vectors V and W. Okay, so I want to talk about inner product V W. Okay, so what do you think I should do? Let us look at V plus W. This norm squared is sum of F of V plus W whole square. Do you understand this? Because this is a vector X. Okay, norm of X equal to norm of Fx. Right? But what is norm of Fx? Therefore, X squared, norm of X squared should be this. Therefore this. Okay, but what do I know about F? F is linear, therefore this is F of V plus F of W whole square. Right? Now I can use inner product. This fellow is nothing other than V plus W, V plus W. But what is this? This is VV plus same thing as WW, and since a real inner product, this is nothing other than 2 times VW. Right? V with W, W with V because of symmetry. And what is this fellow? F of V plus F of W plus F of V plus F of W. That is equal to F of V and F of W plus, again due to symmetry, F of V with F of W. right? But what is our assumption? This norm b squared and this norm fp squared, they are equal. Therefore this cancels with this. These two are equal, right? And therefore these sides are equal. But this object is same as this object. This object is same as this object. Therefore I conclude norm of VW equal to, inner product of VW equal to inner product of FP/FW. So we have proved it. Yeah. So what have we shown? If F is a linear map from a finite dimensional, did I use it's a finite dimensional? I didn't use it here, right? Check that. I never used it. Finite dimensional here, so it is superfluous. So if V is an inner product space, if F is a linear map from V to V which preserves the norm meaning this, right? Then F preserves the inner product. This is we proved only in the case of real inner product spaces. Now how will I prove for complex inner product space? Go back. So I am going to indicate the proof. I am not going to write everything. Okay, this fellow will not be this. This will be this fellow will come as BW plus inner product W with V. But W with V is BW bar. So this is a complex number plus bar. Therefore, it is nothing other twice real part of BW. Right? Similarly, this fellow will become twice real part of inner product FP/FW. So from this we have concluded real part of this is same as real part of this for every VW. Please pause, review, proceed. Make sure you understand this. So now I want to prove imaginary part. See, I want to prove inner product VW, this complex number is this complex number. What I proved is the real parts of these two numbers are the same. How will I prove their imaginary parts are the same? If I prove that, that's okay. How will I get an imaginary part? What is the trick I have to use? Okay, you have to learn to think. How will I get it? Instead of V plus W, what do you think I should do? V plus IW, that's it. Okay, now do the same analysis with V plus IW. V plus IW. This is a vector. This vector is same as V plus IW, F of V plus IW. Right? Now remember, F is linear, but it is a complex linear. Right? Now it's a linear map between two complex vector space. Therefore, this fellow is F of V plus I times F of W. And similarly F of V plus I times F of W. Now, and similarly this one. This is going to be therefore VV and I. This I will come as minus I. Therefore minus I squared is 1. Therefore WW plus this V with IW. This will come as minus I with VW. This V and IW. And this IW will come plus I with WV. Right? Similarly on the other side. But what is this fellow? This is nothing other than complex conjugate of this. Right? Are you following? So this will give you imaginary part. Same way this will give you imaginary part, and you can equate them. So I leave this as an exercise. This will make sure that you follow all the proof. Okay. Okay, so I forgot. So this one for complex inner product space, how will I prove that? Okay, so here you take inner product VW, therefore inner norm of V plus W squared is inner product VW, V plus W plus V plus W, but that is same as inner product FP plus FW. Why is that? Because F is linear. So equating them, you get inner product of BW equal to inner product of FP FW in the case of real. In the case of imaginary, I will get only real part of this inner product BW equal to real part of inner product FP FW. Yeah, you understand? Right. Now for complex, what do you think I have to do? In place of B plus IW, I take B plus IW and carry it out. So I will get only imaginary part of inner product BW equal to imaginary part of inner product of FP FW. Okay, carry that. That's an exercise. Okay. Okay. So what happened to my thing? So what have we shown now? We have shown that in any inner product space I have proved something. What is that I have proved? If F is a linear map from B to V, whether it's be a real vector space or complex vector space, and be it finite dimensional or infinite dimensional, I don't care. If it preserves the norm, it preserves the inner product. Yeah, but in the case, earlier case, I have to assume it's finite dimensional. What did I assume? F is a finite dimensional inner product space. F is a linear map. It carries an orthogonal basis to orthogonal basis. Then I proved F is orthogonal or unitary. Alright. So I have proved the following theorem. Let V be a finite dimensional inner product space over F, where F is R or C. Then the following are equivalent. Yeah. 1. F is inner product preserving, which is same as saying orthogonal or linear. And 2. F carries an orthogonal basis to an orthogonal basis. And 3rd, F preserves the norm. To prove 1 and 3 are equivalent, we don't need the fact B is finite dimensional. Okay, I hope you enjoyed. Go through the proof. We will meet again.